A very warm welcome in the class of Mathematics 1. Today our topic is Rolle's Theorem. Myself Rupak Bhattacharya, Assistant Professor, Department of Mathematics, GIS College of Engineering. In this particular topic, we have some prerequisites, and this will be actually applicable and useful for solving the problems related to Rolle's Theorem as well as to conceptualize this particular topic. So they are, first of all, the concept of function. We all know this, but still we should revisit this particular idea, that what we understand about function in mathematical sense, as well as what are the related terms with this function like domain, range, codomain, and some examples related to this. So we must prepare ourselves along with this particular concept before entering into the discussion of Rolle's theorem. Second, we need the concept of continuity. Obviously, it is the extension of the idea of function and its properties, because when we are applying this term continuity, it is obvious that the functions are there which are continuous and there are some functions which are not continuous. And we also have some variations related to this particular thing, which is very much needed to perform the problems related to Rolle's theorem. Next, we go to the next prerequisite is differentiability. It is obviously the next step of this particular discussion. That is, after learning the ideas of functions and continuity, obviously within that we have to revisit also the concept of limit, and we are talking about the function of single variable over here. We need the idea of differentiability also. So after gathering all these, rather after brushing up all these ideas, we can enter the idea of Rolle's theorem. So let us start this business. Initially, before going into the discussion or deliberation of Rolle's theorem, what is that? Before that, we just want to learn, or rather, we just want to identify some properties of these two pictures. So, if we see these two pictures, what we can get some conclusion for this. Look at this. This is our x-axis, and this is our y-axis. Okay. Now, this blue line is the pictorial representation of the function fx. Y is equal to fx, and it is now given as in explicit form. Sorry, in implicit form. No explicit form is given because we are just looking at the pictorial representation. Now, can we say that there are 2 points A and B on x-axis such that their functional values, we can say it as fa, and we can say it also as fb, that their functional values are same. So this is our first observation we can make over here. Second, we can see from the picture that the function fx is continuous. At least we can say that it is continuous from this particular point to this particular point, as well as we can see that as it is a smooth one, we are seeing the differentiability property also. So now all of us, we can understand that why those prerequisites are there in this particular topic. But till now, take it as a story. It is just nothing but the linguistic representation of this particular picture and identification of the properties from this picture. But after all these things, there is a point C, and if we can just identify the position of C, C is within A and B, in between, and at a point C, we see that one tangent is drawn, and this tangent is parallel to our x-axis. And from the idea of the differentiation, so at this point, the differentiation of fx, that is f dash x at x equal to c, we are getting the value as 0. So it is written as f dash c is equal to 0. So these are some observations we have made. I don't know till now that from what which are coming. So we will coming into this particular discussion after some time. And similarly, if you go for the second picture, if I just completed the first one, then we are going to the second picture. And in the second picture, what you see, that it is nothing but the coining up of these particular ideas. Sometimes if we just check it from this point to this point, or this point to this point, or this point to this point, then actually we are getting the more than one example of the previous thing. It is just like something like that. We are getting some variations of this particular idea in a single frame. So what you see, if I take it in a broader way, that it A and B, then we are getting C1, C2, C3. That means more than one points. But this property is maintained. I think you can all observe that C1, C2, C3 all are within A and B, and the tangents at those points are nothing but the parallel one. Tangents are parallel to x-axis, and that is why f dash c1, f dash c2, f dash c3 all are 0. So very important observation you can make, and you can ask that question, that if we consider the first part, only this part, then this if A is equal to FB property is not valid over here, because A is here, there is a point B, if I take, or B1, it is upper than this. But can't we take A shifted from this point to this point, so that we can get another point B, so that this FA and this FB are same, and then you can get another point C1 over here, where the tangent is parallel to our x-axis, and we can claim f dash c1 equal to 0. So this whole story, single one and the plural one, together with gives us one beautiful observation in mathematics. So let us deal into that. You are getting three statements. It is written in the mixed up direction, that is theorem 3 is first, then theorem 1, and then theorem 2. You can think that what is this? Okay, no problem. In the sequence what it is presented, please check it out. Theorem 3 tells us that it is our Rolle's theorem, that is our topic of discussion for today's class. And it tells us that suppose if we take y is equal to fx is continuous at every point of the closed interval a to b. So I think all of you know what is closed interval a to b. Closed interval is nothing but all the points including the boundary points, that is a and b. So we can take it as x is less than equal to b, greater than equal to a. So we are considering about this particular interval. So fx is continuous at every point of the closed interval ab. This is our first observation. Then the second observation is that it is differentiable at every point of its interior open interval a and b. That means we are not considering its status on the boundary points. It may be differentiable, it may not be. But this differentiable condition is our second observation, what we have made in the last slide. And finally, if fa equal to fb, This is our third observation, what we have made in the last slide. So these three observations already we have made, and Rolle's theorem tells us that then there is at least one. That means there may be more than one, but there will be at least one. It is guaranteed that a C in A and B at which f dash C is equal to 0 means you will get one C such that f dash C is equal to 0. Now if you go back and if you just think about this particular presentation, that fa is equal to fb, it is continuous in the whole interval including a and b, and it is differentiable in the open interval a and b, then we will get a c within a and b at least, so that f dash c will be equal to 0. And it is the concept of exactly one, it is the concept of at least one, because here we are getting more than one. Now then why theorem 1 and theorem 2 is written? Because theorem 1 and theorem 2 actually are some informations which will substantiate this theorem 3. Actually theorem 1 tells us, the extreme value theorem, that if f is continuous on a closed interval like our function in Rolle's theorem, then f attains both an absolute maximum value and an absolute minimum value in a and b. That is, there are numbers x1 and x2 in a and b with fx1 is a small m and fx2 is capital M, and all the functional values fx will be greater than equal to small m and less than equal to capital M. This is actually the extreme value theorem, and this is guaranteed if fx is continuous on the closed interval. So if it is continuous in the closed interval, then it must have one maximum value and one minimum value. It may go like this, no problem. If I consider up to this one, then look at this, it is my maximum value, it is my minimum value. And theorem 2 tells us, the first derivative theorem for local extreme value, what you most probably had the idea in your 11-12 days, that if f has a local maximum or minimum value at an interior point C, then f dash C will be equal to 0. So that is why these 2 points are required in Rolle's theorem. That is why theorem 1 and theorem 2 are mentioned over here to validate Rolle's theorem. Okay, now proceeding further, we are getting 3 diagrams. These 3 diagram tells us something special. First one is discontinuous at an endpoint of A and B. If you check the first one, then if you consider this closed interval A and B, then you will check that the functional value of f at A is this, and the function starts from A plus epsilon from this point, so we get a discontinuity over here. That means this is nothing but the violation of the requirement of Rolle's theorem. Clear? So here you see that f equal to fb, but as it is not discontinuous, you are not getting a point C for which f dash C is equal to 0, means you are not getting some picture where the tangent is something like that, that is parallel to x-axis. Why we don't get? Because there is a violation in the requirement of Rolle's theorem. Similarly, if we go for the second picture, we get that there is a discontinuity at an interior point. This interior point is our x0. So what is happening here? You get f equal to fp, but at x0 there is a discontinuity, and for which again you are not getting f dash c equal to 0. That means here also f dash c not equal to 0. You don't get. And because of the same reason, that there is a violation of the requirements of Rolle's theorem. And finally, you can come to the third example. It is very important because it is continuous in the whole closed interval A and B. But our second requirement, that is, though f equal to fp, but we need it has to be differentiable in the open interval ab. But what we get at point x0 over here, there is a sharp edge at fx, and this sharp edge indicates that the function fx is not differentiable at x0 because it is having not a not an unit tangent at this particular point. So all these three are examples of the violation of Rolle's theorem's requirement, and that is why we are not getting any point C within A and B, so that f dash C is equal to 0. Okay, so now if we proceed, we will get one very good example related to these problems. This example tells us that we have to show that the equation x cubed plus 3x plus 1 equal to 0 has exactly one real solution. When it is a cubic equation, it is having three solutions, but we have to show that it will have only one real solution. How to find it? The solution is given explicitly over here. So the continuous function is defined like this. Now f of minus 1 is equal to minus 3 if we put the value over here. And if we put f0, means x equal to 0, it will be 1. Now the intermediate value theorem tells us that the graph of f crosses the x-axis somewhere in the open interval minus 1 to 0, because at minus 1 it is negative and at 0 it is positive. So obviously from negative to positive, when it will go according to this particular range, then it must cross the x-axis. Then the derivative f dash x for this particular function is 3x square plus 3, and it will be never 0 because it is always positive, because it is a square term. So whatever the value of x you are going to take, it will be positive. Now if there are even 2 points at x equal to a and x equal to b where fx was 0, because we have to check how many solutions are there, and we are assuming that if there are two real solutions, that is x equal to a and x equal to b, then Rolle's theorem actually guarantees the existence of a point x equal to c in between where f dash were 0. So if there are 2 points a and b for which they are 0, that means their functional values are same. So Rolle's theorem will give you a point C where your f dash C is equal to 0, but already we got this clue that f dash C will not be 0 within this range minus 1 to 0, because f dash x is having the expression 3x square plus 3, which is always positive for all possible values of x. So we get that there will be no more than 1 0. So only one real solution will be there. So look at this. This is not the proof of Rolle's theorem. This is not the direct verification of the function for Rolle's theorem, but this is a very important application of Rolle's theorem through which we can guarantee that how many roots are there. So we will now proceed for some problems related to Rolle's theorem. First of all, we are now going to check whether the Rolle's theorem is applicable or not. The first problem is fx is equal to 1 by 2 minus x square, and the range is given -1 to 1. Clear? So Rolle's theorem is applicable or not means we have to check here the requirements are satisfied or not. Clear? So here this function fx, it is clearly continuous at you know that you have to check it for the closed interval. So from -1 to 1 it is continuous because it is defined in this particular range. So what we can do, we can find out the differentiated expression of this. It is -1 into 2 minus x square. It was whole to the power -1, so it will be -1 is coming in the forward part, and 2 minus x square whole to the power -2. And then next you are differentiating minus x square, so it will be -2x. Okay. So simplifying this, what we can get, this minus and this minus will be cancelled out. 2x by 2 minus x square whole square. Now obviously it will exist because the problem if will be there, that is 2 minus x square is equal to 0, and we are getting the range over this, so -1 to 1 in this particular case it is existing. Now finally we have to check what is the value of f of -1 and what is the value of f of 1. So f of -1, if we put it, we will get it 1 by 2 minus 1, that is 1 by 1, that is 1. And if we find out f of 1, then also we will get it 1. So what we get, f of -1 is equal to f of 1. So look at this, all the requirements which are needed for verification of the Rolle's theorem, all are satisfied. So this one is satisfied, the differentiation part is satisfied, and the continuity part is also satisfied. So we can say that Rolle's theorem is applicable to this function in this interval. So we can say that it is okay. In a similar manner, you can proceed for some other problems of this type also. Just for example, if we get that our function fx is now suppose 1 minus x to the power 2 by 3, and the interval is given -1 less than x less than equal to 1, that is the same interval like this. So now here also the job is same. First of all we have to check that the continuity, and what we get, that if dash x is equal to -2 by 3 x to the power minus 2 by 3 minus 1, that is -1 by 3. If you want to see it in this manner also, then also you can write it as then 1 by x to the power 1 by 3. But the problem is at x equal to 0, f dash x does not exist. Why? Because you can see that the denominator part is becoming 0. Obviously the existential criterion is not satisfied. So what you can say, that though we need that within this interval our function has to be differentiable, but we are getting the differentiability criterion is not satisfied. So for this function, for this interval, Rolle's theorem is not applicable. Here, this is the way through which we can make our idea strong. Now, in the similar manner, some verification of other problems related to this Rolle's theorem may appear. Uh, Actually, in these cases, you have to find out sometimes that when the function is satisfying all the conditions, then you can find out the value of c for which you are getting f dash c equal to 0. Like you can take a function fx is equal to x cube minus 6x square plus 11x minus 6, and the interval is 1 2 3. So what you have to do, your job is to first of all find out all the requirements are satisfied or not, and is it a polynomial function, the continuity problem and the differentiability problem will not be there. Our job is to check whether the value of f1 is 0. If we put 1, 12 and 12, and what is the value of f3? If you calculate, you will get it at 3 to the power 3, 27, and here you are getting 33, so 60, and here 9 into 6 54, and 6 60, so it is also 0. So what you are getting, f1 is equal to f3, and the requirement for continuity and differentiability is validated because of the polynomial form of this function representation. So we know that according to Rolle's theorem that there will be f dash c will be equal to 0. So what will be the value of c now for which you are going to get this one? Now it is a simple problem, because f dash x is equal to 3x square minus 12x plus 11. Okay, so f dash c will be 3c square minus 12c plus 11. Now if you have to make f dash c equal to 0, your job is to make 3c square minus 12c plus 11 is equal to 0, and solving which you can solve it by middle term factor, you can solve it by your observation, Sridharacharya's rule, whatever you are comfortable. You will get the value of c is equal to 6 plus minus root over 3 by 3, which is nothing but you can write the values as 2.57 and 1.42. After a calculation I got this, you can also calculate it very easily and you can check it out. So what you get, you need at least one, you get more than one, no problem. But Rolle's theorem is verified, and using Rolle's theorem you can find out also the point C for which you will get this is 0. So this is the overall idea and the basic constructions for Rolle's theorem. Now these are the references what we have used to prepare this video lecture, and we have taken some problems from these resources. And finally, these are the assignments. You can start solving it and you can do it. And finally, I want to thank you all. Happy listening, happy learning.